Okay, so in the last lecture, what we did was we tried to apply the Biot-Savart law for two different types of cases. The first one was basically the most complex one, in which we tried to calculate the value of H for a current carrying conductor whose length is quite large as compared to the distance from which the value of H was to be measured. And for that case, the most complicated thing about that example was converting all of our uh, given parameters into theta's perspective, and after that transforming back from theta's perspective to in the terms of the things that we have been given by uh, the numerical or by the author. The next example was basically the calculation of magnetic field intensity H for a pi-shaped loop, and for that case we took a look at how the contribution of H for the straight conductors was zero for that loop, and the contribution of current in the curved path of that pi was basically the one which was responsible for all the magnetic field that was being generated by that loop. In this lecture, we'll try to solve another example, and this example is also pretty complex in terms of some things that there might be some kind of things that you don't get from this lecture. So I'll suggest you to please divert all of your attention towards uh, these things that I'm trying to explain. So the example is basically related to the calculation of magnetic field of a circular loop, current carrying circular loop. So what's happening here is basically that he is saying that we have a closed circular loop which carries the current in it, a steady amount of current I in it, and we need to calculate the value of magnetic field intensity H at a point which is above that circular loop, which is above the pivot point of that circular loop. This example corresponds to the example that we studied in electrostatics, and the example was more related to the calculation of the value of electric field intensity uh, due to a ring of charge. This also corresponds to the thing that I gave you in an assignment in which you had to calculate the value of electric field intensity at a certain point. We'll be talking about that in this example also. But the thing that you need to understand right now is that what is it that the author is asking from you, what is it that the examiner, that the author is asking of you. So he's saying that we have a closed circular loop. First of all, what we'll do is we'll try to draw the reference frame. So this is the z-axis, this is the y-axis, and this is basically the x-axis, x-axis, y-axis, and this is z-axis. So he's saying that we have a circular loop which is placed at the origin. I hope I can draw a circular loop. This is basically a circular loop which is carrying current. Okay, so this is the circular loop, although its orientation is a bit messed up in this drawing because it has to be symmetrical. Let's just say this feels to be the center of the circular loop. Okay, so this is the z-axis. Okay, he's saying that the current is flowing in this direction, and the radius of this circular loop is small a, and the angle that it makes from x is basically phi, as we know, and we have to calculate the value of dh, or the value of h basically at this point. This point is 0. I can't write it here. The coordinates at this point is 0, 0 and z. Okay, 0, 0 and z. So this point is basically at the axis of this thing, and but it's above the circular loop. So yeah, this is what he's asking of us. So he's saying that please calculate the value of dh at this point p. So how do we calculate the value of dh at this point p? We know that according to Biot-Savart law, we have 4 pi r square, and then I, then here we have dl cross r hat. So these are the things that we need to calculate. So first of all, we need to calculate the value of r, this thing. So what is the magnitude of r? We'll draw, if this is dl, because we have to take dl according to our own requirement. So this is, if this is dl, what will be the vector r? This is going to be, this is the vector r, which points from dl towards the observation point, and this is basically the base. So this is a, and we can call this as, this is, this side is along the z-axis, we can call this side as z, because he's given us that the point, the coordinates of this point is 0, 0 and z. This means that this side is basically z. So we can say that the magnitude of r is basically a square plus z square under root, a square plus z square under root. Okay, so there are two things that we need to calculate about this scenario. First of all, we need to calculate the magnitude of dh, and after that we need to calculate the direction of dh. We'll try to calculate the magnitude of dh first, and then we'll move on towards the direction part of this thing, because the direction part is pretty complicated. So if we talk about the magnitude of dh, this is going to be I over 4 pi r square, and then magnitude of dl cross r hat, and we have calculated the value of this r. This is a square plus z square under root, so we can write this as 4 pi and then a square plus z square. And if we are taking the magnitude of dl cross r, then that magnitude will be the magnitude of dl, because there is no magnitude of r. The magnitude of r hat is basically 1. So this is the magnitude of dh that corresponds to this particular type of scenario. Now we'll move on towards finding to the direction of dh. We can see that the direction of dh is always perpendicular to the plane which is carrying r and dl, the plane which is carrying this r and the dl vector. Now this is r and this is dl vector. Okay, so if this is r and this is dl vector, he is saying that dh basically has to be perpendicular to both these vectors. So if we draw dh like this dh is basically perpendicular to this also, and this dh is basically perpendicular to this thing also. Let me draw this just like this. If we see it from here, we'll see that this is dh and this is dl, and if we draw this dh here, we'll see that this is dh and this is dr. Okay, so now dh, if we draw dh like this, which is perpendicular to this thing, which is perpendicular to this r, absolutely perpendicular to this r, this is going to be the direction of dh, and this dh is basically perpendicular to this r because we have drawn it perpendicular to dr, and the dl will be just like this, and it will be perpendicular to dl2. So this is basically the direction of dh. He is saying that this dh, if we take a look at this thing, this is the r, it has one component in small r's direction and the other component in z's direction. So he can, if we're talking about cylindrical coordinate system here, this is r's direction and this is z's direction. Similarly, if this thing is perpendicular to r, it means that it also has two components. One component will be in r's direction and the other component will be in z's direction. So we'll draw those components. This is the component of dh which is in z's direction, we'll call it dhz, and this is the component of dh which is in r's direction, so we'll call this dhr. So now we have specified the direction of ds, and we have further divided that dh into its rectangular components r and z. He is saying that dh is basically in rz plane, so the components, the rectangular components that dh will have, will be in r and z's perspective. So this is the thing about this dl. Now if we consider another dl which is on the opposite side of this thing, just like we did back in that example in which we had been given with a ring of charge. So in that case, we'll call this dl as dl dash, and we'll draw the r from this thing. So we'll see that this is r dash. Once again, we will have another dh here. This is dh dash, and that dh dash will also have two components. Well, one will be in r's direction and one will be in z's direction. So if we take a look at this scenario, we have two components which are supporting each other, and we have two components which are cancelling each other. So we can say that the dhr dash, dhr dash and dhr, they'll cancel each other. So the net magnetic field will have to be in z's direction. So we figured out that the net magnetic field has to be in z's direction. So we figured out the direction of magnetic field. So if we write the expression for magnetic field, and due to this dl, we'll say that dh is basically z hat and dhz. Okay, so what's the value of dhz? If we talk about the value of dhz in terms of dh, because we haven't been given the value of dhz, we have been given the value of dh, so we have to calculate the value of dhz in the form of dh itself. So what will be the value of dhz? For that, we need to see it in the perspective of the angle that it's making. So if this is the angle theta, okay, if this is the angle theta, the other theta will be here, and if this is theta, the other theta is going to be here. and if this is theta, the other theta is going to be here. So this basically theta is the same angle which is this thing. This is pretty easy to understand if you draw this like this. If you have this thing, if you have this thing, if you have this thing, and you have this angle. Okay. So now what you have done is you have drawn a perpendicular line which is perpendicular to this hypotenuse. So as this line is perpendicular to this hypotenuse, then it means that it will make the same angle theta with this line. Okay, you can calculate this according to the procedure that I have told you before. That's very easy. You can uh, give the angle, this angle, a name of x, and you can see this is 90 degrees, so you can say 90 plus theta plus x, this is equals to 180 degrees. You'll calculate the value of x, and then you'll put this value, you'll say this is y, then you'll calculate the value of y, and after that you'll put this value as z, and you'll calculate the value of z. Whenever you calculate the value of z, you'll see that this will come out to be equal to theta. I have we have done this before, so I'm not doing it again. Just for the logic sense, I'm telling you that if this vector is perpendicular to this hypotenuse, then the angle that it makes with the same line, it is going to be equal to this angle that it makes with this straight line. So he's saying that this, if this is the angle theta, that means that dhr is basically going to be dh sine theta, and dhz is going to be dh cos theta. So he's saying that z hat dh and cos theta. Once again, we'll put the value of dh. This is basically the magnitude, so we have calculated the value of magnitude, I over 4 pi a square plus z square, and then here we have cos theta. So right now we have this equation, but still there is something wrong with this equation. I forgot to write dl, this dl. There is something wrong with this equation. What is wrong with this equation? We have a theta's value here, and we have not been given this theta, so we have to convert this theta into a more familiar form, into something that we can mention in small a, z, or r, the things that we have been given. So we'll do that later. First of all, we'll take integral. We will take, because we have calculated the value of dh, but we need to calculate the value of h. So if we take integral at both sides, and we'll say h is now equals to z hat I cos theta over 4 pi a square plus z square, and integral of dl. This basically integral of dl, this is a closed circular loop, so we know that for a circle the whole integral will equal to 2 pi a. This is the circumference. Okay, so this 2 and this pi will be cancelled by this, so this thing will become z hat I cos theta divided by a is above that 2 into a square plus z square, this thing. And if we want to mention this cos theta in the form of a and z's, then we'll take this triangle, and what will be the value of cos theta? Now a over hypotenuse r, which will be a square plus z square under root. So we'll put the value of this cos theta into this expression. Let me just remove this. Z hat I a over 2 a square plus z square and here it is a over under root a square plus z square. So this thing will now become z hat I a square over 2 into a square plus z square 3 by 2. This is the value of h. Okay, and there are, this is basically the answer, because we have calculated the value of h in terms of all the things that were given to us. I was given to us, a was given to us, z was given to us. We can put in the values of these things into this equation and we can calculate the value of h for this ring of charge. But there are two special cases. At The one special case is when we are calculating the value of h at the center of this loop. There is no z. Okay, for that special case, when z is equals to 0, the value of h will be z hat I over 2a. We can put the value of z to be 0 here, and it will be easy for us to modify or simplify this this equation for this special case. And there is another special case in which he says that z square is too much as compared to the a square. This means that this observation point is too far away as compared to the radius of this ring. We are measuring the value of h from a lot of distance as compared to the radius of that ring. At that point, this thing will overwhelm. Where is this? This thing will overwhelm, and this a square will have to be ignored. And for that case, the value of h is going to be z hat I a square over 2z ka magnitude, for the case when z is for greater than the value of a. So this is it for today. If you take a look at um, this is it for this example. If you take a look at this example once again with a different perspective, you know that whenever you were calculating the value of p, you were saying that you were above the ring that contained the steady current I. When you were here, the value was z hat. When you were here, the value was z hat. The thing that I want to ask you is, what if we have the point which is below this ring? Well, the direction of magnetic field intensity that we'll find out, will that be the same beneath the ring, or will that change? You'll have to think about this, and we'll have a discussion on this thing. I think this is a good thing to debate on. We'll see what have you got through this, what have you gotten through this example, and we'll see that if you can guess the right answer to this question. uh, okay, after this we have a topic which is related to magnetic field of a magnetic dipole. Basically, he is talking about magnetic dipole. What is a magnetic dipole? We have discussed the electric dipole. We have discussed the magnetic dipole in terms of north and south poles. So we have to understand what a magnetic dipole basically is. He's saying that we have calculated the value of h for a current carrying loop. He's saying that a current carrying loop with the dimensions much smaller than the distance between the loop and the observation point is basically called a magnetic dipole. How will this be considered as a magnetic dipole? Basically, what he's doing is he's referring to the same thing that we have discussed in the last example. He's saying that if we have a circular loop like this, if we have a circular loop like this, and this circular loop is basically uh, carrying a current which is flowing through this circular loop, he's saying that if this is the direction of I, he's saying that what will be the direction of magnetic field intensity. We We measured that magnetic field intensity's direction at this point. We measured that magnetic field's direction at this point. At this point, it was in the z's direction. At this point, it was again in z's direction. So the magnetic lines of force will turn out to be like this. At the middle of this, the lines will be like this, and at this point, the lines will be like this. At this point, the lines will be like this, and at this point, the lines will be like this. They're going out, they're going out, and at this point, like this. At this point, it will be like this. All of them will return back. I've talked about it earlier. Okay, so these are going to be back after covering a lot of distance as compared to this one at the edge. So inside, this will be upward, outside, this will be downward. Similarly, in this case, this side is upward. How are we calculating this? Well, we are using the right hand rule. If we point our thumb in the direction of current at this point, the fingers curling will give us the direction of magnetic field. So if the thumb is pointing into the screen, the fingers are giving us the direction of magnetic field, which is clockwise in this case and anti-clockwise in this case, because in this case our thumb will be directed out of the screen. So what we're seeing here is that in this case, in left hand side of this ring, the lines of force are basically coming out, and in right hand side of this loop, the lines of magnetic field intensity are basically coming into the loop. So he's saying that this is one pole and this is the other pole. He's saying that basically this loop, this current carrying loop, is a magnetic dipole because it has two different poles. Otherwise, you can see it as this two. If you are seeing it from here, you'll see that all the lines are coming out, and if you'll see it from here, you will see that all the lines are coming in. This is pretty similar to what we have observed in a bar magnet. In a bar magnet too, if you can remember the experiment in which there were different type of iron segments, the small pieces of iron fragments, and you put the bar magnet on top of those fragments, iron segment fragments which were free to move. They took the shape of these lines of force. This means that we had a pretty similar type of phenomena there too, just like this. The lines were coming out of the North Pole and they were going in through the South Pole. This means that we had two poles. So what he's saying is that the magnetic dipole exists wherever there is magnetic field. Just as in contrast to the electric lines of force, because in electric lines of force, it was not necessary for a magnetic dipole to exist, because there could be a single positive charge and the lines should be emitting from that positive charge, but it wasn't necessary that there has to be a negative charge around it somewhere too. But in case of magnetic fields, that like we have talked before, in case of magnetic fields, the line of forces are always in the form of closed loop. We'll study that in the Gauss's law of magnetism too. So he's saying that a current loop with dimensions much smaller than the distance between the loop and the observation point is basically called a magnetic dipole. The pattern is similar to both bar magnets. And if we talk about magnetic dipole that we studied in one lecture before, that magnetic dipole moment was equals to n hat nia. He is basically saying that this is the magnetic moment of a current loop with a single turn. If we don't have n, if m is equals to n hat ia, he's saying that this is the magnetic moment of a current carrying loop which has a single turn. If it has multiple turns or n turns, then will correspond to the second expression. So he's saying that, so for one, for the one shown previously, m is equals to, in the last example that we studied, we mentioned the magnetic field intensity to be z hat I a square over 2z cube. This is a special case which we are talking about here, in which the value of z was too much as compared to the value of a. He is mentioning this basically in the form of magnetic moment. So he's saying that m is basically I pi a square. So he has mentioned this for this particular scenario, I pi a square. Pi a square is basically the area, and I is the value of current. Because it had a single turn, so we have put the value of n to be equal to 1. So this is I pi a square for this scenario. So if we want to mention the magnetic field intensity in the form of magnetic moments, in the form of magnetic moment, what do we need? We need the value, we need I, we need a square. We have both these things, but we don't have pi, so we'll multiply and divide this thing by pi, 2 pi z cube. Now this is equals to m. So m over 2 pi z cube, and if we enter this unit vector into this m2, so this m is now a vector, m is equals to, this is how we mentioned the value of magnetic field intensity in the form of dipole moment. But he is saying that this expression applies for a point which is very far away from the loop. But the one thing that is not generic in this case is that what we did in the last example too, is that the point was always on the axis. The point was here, the point was here, the point that we need to debate on in the interactive session was here. It always was on the axis. What if the point is not on the axis? What if the point is somewhere here, and we want to calculate the value of h at this point? We are not calculating the value of h at a point which is placed at the axis. We are calculating the value of h at a point which is not at the axis. So we need to have a generic value for that too. So he's saying that for that case, we will refer this example to the example that I gave to you in your assignment. For that case, you will apply the same approach that you did apply in that assignment to this scenario, and as a result, you will see that the value of h will come out to be m over 4 pi r hat ka square, r hat ka cube, sorry, and then r hat 2 cos theta plus theta hat sine theta. So the students which did that assignment on their own without cheating, and they understood what was in that assignment, whenever they will look at this expression which is given right here, they'll understand how this equation was derived. And the ones who did not do that assignment on their own, they'll need to do that once again on their own if they want to understand how this expression came out to be. Because this expression can be asked in your exam, because this was a part of an assignment that was given to you. So I hope you have understood everything. If there is something that you need to ask, you'll you will be welcome to ask that in the interactive session. This is it for today. Thank you so much.